Now, in module 3 of chapter 9, we shall learn another new concept, that is principal curvatures of surface. In module 2, we have seen that normal curvature kappa n is equal to b alpha beta du alpha du beta by a alpha beta du alpha du beta. That means, these normal curvatures depends on the directions of du 1 du 2. So, in this module, that is module 3 of chapter 9, we shall learn about the directions which have the extreme values. So, the directions of the normal curvature which have the extreme values is known as principal directions, and the curvature at the points is called principal curvatures. So, let us see the definitions and deductions about the principal curvatures with some interesting examples. So, in module 3 of chapter 9, we shall learn about the principal curvature of a surface. Now, how this concept of principal curvature is coming, let us see. So, we state the definition of the principal curvature of a surface, that the normal curvature of a surface depends on the direction du 1 du 2, because in our previous module, that is module 2 of this chapter, we have seen that normal curvature is equal to b by a, where b is the second fundamental form and a is the second fundamental form, and b means that is b alpha beta du alpha du beta by a alpha beta du alpha du beta. That means, kappa n, that is the normal curvature, depends on the direction of du 1 du 2. And here we shall find out the directions for which kappa n has the extreme values, and these directions, where the directions have extreme values, these directions are called the principal directions at the given point, and the corresponding values for kappa n, that means the values of normal curvature for these directions, principal directions, are called the principal curvatures. Now, let us denote kappa n by kappa p or rho, whatever we can say, for principal curvatures. Now, the equation kappa n equals to b alpha beta du alpha du beta by a alpha beta du alpha du beta. We have obtained this one in our previous module. So, we can write this one by in this form, b alpha beta du alpha du beta minus kappa rho a alpha beta du alpha du beta equals to 0. Now, as we are finding the principal curvature, so we are writing or replacing kappa n by kappa rho. Now, differentiating with respect to u alpha, we get b alpha beta du beta minus kappa rho a alpha beta du beta. Or if we take du beta common and divide by ds, then it will be b alpha beta minus kappa rho a alpha beta lambda beta because lambda beta we know it is du beta ds. So, we write b alpha beta du beta minus kappa rho a alpha beta du beta in the following format: b alpha beta minus kappa rho a alpha beta the whole into lambda beta, that is equal to 0. Now, this is a set of homogeneous equations and will possess non-trivial solutions for lambda beta if and only if the values of kappa rho are the roots of the discriminant equation, this one. This is the discriminant equation of the previous equation, that is the determinant of b alpha beta minus kappa rho a alpha beta equals to 0. Now, if we expand this equation, because alpha beta is running from 1 and 2, we know that one. So, expanding we get b11 minus kappa rho a11, b22 minus kappa rho a22 minus b12 minus kappa rho a12 whole square equals to 0. Just if we expand the previous equation, we get this one. Now, arranging and breaking the square term and arranging, we get kappa rho square into a11 a22 minus a12 square minus kappa rho this term a11 b22 plus a22 b11 minus 2 a12 b12 plus b11 b22 minus b12 square. So, arranging we get this equation. Now, we know that a11 a22 minus a12 square can be written as a, because it is the determinant of a alpha beta, and in the last term also the same thing, b11 b22 minus b12 square can be written as b, that is the determinant of b alpha beta, and the middle term is this one. So, the previous equation takes the form this one, a kappa rho square minus kappa rho a11 b11 plus a22 b22 minus 2 a12 b12 plus b equals to 0. Now, if I divide by a through all terms provided a not equal to 0, we get this relation kappa rho square minus kappa rho a11 by a b22 plus a22 by a b11 minus 2 a12 by a b12 plus b by a equals to 0. Now, a11 by a, that is actually a22, that is the reciprocal tensor of a11. Similarly, the other terms, and so this equation takes this form. So, this one, the middle term, can be written in tensor notation as a alpha beta b alpha beta kappa rho. So, the whole equation becomes kappa rho square minus a alpha beta b alpha beta kappa rho plus b by a equals to 0. That means, kappa rho square minus 2h kappa rho plus k equals to 0. So, this is a quadratic equation in kappa rho which have two roots. So, we denote the two roots of kappa rho by kappa 1 and kappa 2 and call them the principal curvatures of the surface, and the directions corresponding to kappa 1 and kappa 2 are called the principal directions on the surface. So, from this equation we get the principal curvatures of the surface and also the principal directions on the surface. And we have this relation that kappa 1 plus kappa 2 equals to twice h, because the sum of the roots is minus b by a, that is 2h, and the product of the roots, that is k, the Gaussian curvature k. The sum of the roots is 2h and the product of the roots is the Gaussian curvature k. Now, from the previous equation, it follows that the principal directions are determined by this equation, b alpha beta minus kappa 1 a alpha beta lambda 1 beta equals to 0. This is for the principal direction for the kappa 1, and also b alpha beta minus kappa 2 a alpha beta lambda 2 beta. This is the principal direction for the principal curvature kappa 2. Now, multiplying the first equation by lambda alpha 2 and the second equation by lambda 1 alpha, and then subtracting, we get this one, b alpha beta minus kappa 1 a alpha beta lambda 1 beta lambda 2 alpha minus b alpha beta minus kappa 2 a alpha beta lambda 2 beta lambda 1 alpha equals to 0. Simplifying the previous equation, we get kappa 2 minus kappa 1 into a alpha beta lambda 1 alpha lambda 2 beta equals to 0. Now, we know that a alpha beta is equal to a beta alpha, because the coefficient of the first fundamental form and the coefficient of the second fundamental forms are symmetric. So, a alpha beta equals to a beta alpha and b alpha beta alpha. So, when kappa 1 minus kappa 2 equals to 0, that means the kappa 1 equals to kappa 2, the point is called an umbilic point. So, if the principal curvatures are same for both the principal directions, then the point is called an umbilic point, and when a alpha beta lambda 1 alpha lambda 2 beta equals to 0, the principal directions are orthogonal. Thus, we can state the theorem that at each non-umbilical point of a surface, here we are considering the non-umbilical point, because kappa 1 is not equal to kappa 2. We are considering that kappa 1 is not equal to kappa 2, because when kappa 1 is equal to kappa 2, we are getting umbilic point on the surface. So, at each non-umbilical point of a surface, there exist two mutually orthogonal directions, because a alpha beta lambda 1 alpha lambda 2 beta equals to 0. So, we get two mutually orthogonal directions for which the normal curvature attains its extreme values. So, in the first section of module 3 of chapter 9, we got another new concept, that is the principal curvatures of a surface. Here we have obtained a very important concept of the surface geometry, that is the umbilic point. We have seen that if two principal curvatures are same at a point, then we get an umbilic point. We have also seen that at the non-umbilical points on a surface, there exist two mutually principal directions where the normal curvatures are extreme. Now, in the next section we shall give some examples, that means some examples of surfaces where we can find the principal curvatures. So, let us see these examples. Now, let us see the equation for the principal curvatures of the surface for the right helicoid. Now, right helicoid has the equation r equals to u cos v, u sin v and c v. So, for this one we have earlier obtained these equations, actually we have earlier obtained. So, we have not given the equation here. A11 is 1, A12 is 0, A22 is u square plus c square. We can easily find these values because these are the coefficients of the first fundamental form, and we can also find the coefficients of the second fundamental form, that is B11 equals to 0, B12 is equals to minus c by root over u square plus c square, and B22 equals to 0. So, if we take the determinant of A alpha beta, that is A, the value of A, and we get the value of A is u square plus c square. And similarly, the value of B, that is the determinant of B alpha beta, is equal to minus c square by u square plus c square. Consequently, the equation for the principal curvatures of the right helicoid becomes u square plus c square kappa rho square minus c square by u square plus c square equal to 0. So, kappa rho is coming equal to plus minus c by u square plus c square. Now, let us see another example, that is we are going to find the principal curvatures of the surface defined by x1 equals to u cos v, x2 equal to u sin v and x3 equals to fu, that is the surface of revolution, and find the condition for the surface to be minimal. We have to find also this condition. Now, here the equation is r equals to u cos v, u sin v, fu. In the same way, we can find the A11 equals to 1 plus f square, A22 is u square, A12 equals to 0, that means the curvilinear coordinate system is orthogonal for this type of surface, where f1 is df du, because f is a function of a single variable. So, we can write f1 equals to df du. So, a11 is equal to 1 plus f1 square, a22 is u square, and a12 equals to 0. So, the value of a is the determinant of a alpha beta, that is 1 plus f1 square 0 0 u square, and it gives u square 1 plus f1 square. Now, if we find the reciprocal tensor of these coefficients of the first fundamental form, we get a upper a11 equals to 1 by 1 plus f1 square, a22 is equals to 1 by u square, and a12 equals to also 0. So, B, the determinant of B alpha beta, is equal to u f1 f11, it is the second order derivative of the function f by 1 plus f1 square, where f11 just I have mentioned that it is the d2f by du2. So, therefore, the equation of the principal curvature, we have seen that it is the kappa rho square minus a alpha beta b alpha beta kappa rho plus b by a equals to 0. That is kappa rho square minus this relation. If we put the values, we get this equation. And the solutions for these two are kappa 1 equals to f11 by 1 plus f1 square to the power 3 by 2, and kappa 2, that is the principal curvature for the first principal direction, is kappa 1, and the principal curvature for the second principal direction is kappa 2 is equals to f1 by u 1 plus f1 square to the power half. If rho 1 and rho 2 are radii of curvature, then we know rho 1 equals to 1 by kappa 1, that is 1 plus f1 square to the power 3 by 2 by f11, and rho 2 is 1 by kappa 2, that is u 1 plus f1 square to the power half by f1. Now, the condition for the surface to be minimal, we know that a surface is a minimal surface when the mean curvature, that is h, equals to 0. So, we know that kappa 1 plus kappa 2 equals to twice h, and that is equal to 0 because h is 0. So, the condition for the surface to be minimal will be this one, f11 by 1 plus f1 square to the power 3 by 2 plus f1 u 1 plus f1 square to the power half equals to 0. That is, if we simplify this relation, we get f1 1 plus f1 square plus u f11 equals to 0. So, in the module 3 of this chapter, chapter 9, we have learned about the principal curvatures of a surface, and we have seen two examples where you have obtained the principal curvatures or the equation for the principal curvatures. From here, we have also obtained a concept of umbilic point. We have seen that on a surface, an umbilic point can be obtained when the principal curvatures are same. So, with these things, we end this module.